Allow me to continue where I took a small what you call interruption yesterday due to or length of the recording. This is continuation of earlier presentation regarding how allowances and tolerances are very critical in relation to engineering drawing. Now say I will switch this on to you. This is a very routine bracket which we often see in our normal what do you call production or maintaining geometrical integrity with respect to all the parts. It looks relatively simple because it is easy for me to what you call make something, and depending on the total amount of number of drawings and all that, we can number of bends which are to be incorporated, we can mention it directly here. Now we come to a very important thing regarding the quality of the work. One part of it which I have spoken to you is about simple tolerancing. Tolerancing we know is all about how to maintain one particular feature, and then during production how variations occur. It may be because of tooling and because of other things like that. However, you need to mention these things as per a international standard. The presentations here are as per the ISO, and more or less everything is maintained. You see here there is a reference to a part A, there is a perpendicularity symbol here, there is a parallelity symbol here, again according to the particular features that is presented here. So when you make the solid model, we have no issue with it. The models get easily done. So I will present to you a model which has been made here. It looks fine, is it not? All I wanted was saying there should be a bush at the bottom portion. This is the bush, and then after that this part of it is the bush. This bush should accept a plunger. So for the while ignore the 0 what do you call the 2 decimal accuracy. It was default, so I left it like that. Most packages they give this default because they were all based on the old inch dimensioning, where it was very critical because it is very normal to go up to 64th of an inch or 30 what do you call 1 by 32 of an inch. Leaving all that, you will discover that in this particular case I was trying to make a part like this. Looks fine, isn't it? But this is where we end up with saying, is it enough if we just make a model and leave it like that, and can anybody actually make anything like this? See here very nicely 54 is shown, there is something called 30 is shown, and then if you go to this quadrant here, life can't be better. But in reality it is not so easy. Please have a look at the part that has been fabricated. This is the actual part that has been fabricated in the workshop. One of the first thing you will see is this piece that has been made here has been made by a different technique completely. So what has been done is a regular full-fledged solid has been taken. Understand, no? It is not part of 2 parts that are assembled together. This whole thing has been machined from a full solid, something of equivalent. Right now I think this one was a 45 mm square. So they have taken the 45 mm square, they have milled a groove, then on the other side they have made a step here. So that the idea being it sits on this hydraulic jack. This is part of a vehicle design which I will show you afterwards. The chassis member sits here. Same thing here with the other thing, and then you will see here This just for the convenience, saying how these things work and all that. And why this to have been shown is, this is the highest position, this is the smallest position. Depending on the amount of raise you require, this is part of a a vehicle chassis. So this has been kept under an electric vehicle chassis, and then you jack it up. Once you operate this hydraulic jack, it has to be raised this much to make sure that this top member engages with the chassis member, and then afterwards lifts the wheels clear of the floor, and afterwards some other safety backup support is there. Now that you have seen the whole, so if you see the drawing, it is not enough if I just mention some dimensions here. Two things are very critical, saying on what basis I have calculated the depth 30 millimeters. This is only a concept drawing. As such, when actually it went to the workshop, the machine shop, somebody there has considered the type of material that is available, the type of material that is used, and various strength aspects. While I was feeling very thrilled that I made a very good drawing here, first thing you will notice is, it is probably inappropriate to take a channel and try to take another pipe, make two operations, and then try to weld these things here, or I try to weld these things all around, and may or may not give me a useful product. In contrast, what has been made there is, it strictly follows a practical approach, meaning somebody has measured all the necessary items and they have fabricated this, and that is much more appropriate, and it is strong and accidentally does not create any problems. In this case, let us say by some mistake this thing gets squeezed together. The moment they get squeezed together, we end up with a useless part. Similarly, there may be a parallelity and such problems, but the design that has been implemented, finally there need not be a problem. The advantage being right now is, once I make the solid model, somebody can remotely work on it. The machine shop people can happily work on it and then get these things ready. And then out of my unending enthusiasm, I have even tried to make something else. Why not take a pipe of a correct diameter, because they are all standard diameters, of a higher gauge, and then just make a slit here, and then bend them together. Once I bend them and make them together, I expect this thing will make a very good device on which I can make a U and put it. But you too would have noticed, what is the point, what are you trying to prove here? Saying except that you know how to make a solid model, it doesn't, nobody has seen any utility of this product. You seen my point? Then where do we have the U? Can I make something out of you? At that point we decided to just leave it, saying don't worry about any of these things. How to make this? This I have shown you earlier. Now, especially in the case of sheet metal, the ISO has spent huge amounts of effort in documenting it. Strictly speaking, something falls in the tolerance zone, and then this is above the tolerance zone. Imagine one end of it falls within here, another end falls here. Now do we accept a part or not? That is where things like parallelism and other features are presented very well here. This is the tolerance zone, something has fallen out of sight. Imagine somebody makes a part, one end follows the one edge of it and another end follows the edge of it. Will you still accept it or not? This is where things like perpendicularity and parallelism are stressed regularly. And the magic is, a simple solid model very rarely seems to take care of these things. You got my point? Why I specifically picked on this is a simple solid model makes something which looks exotic and so on, but in practical operation, depending on the processing and all that, one needs to work carefully towards how these things actually work. This has been so far regarding the sheet metal work, but if you see carefully, this whole concepts of limits, fits and tolerances have derived from circular parts, typically bearings. This appears like a repetition, but kindly bear with me, because even earlier lecture I started with this. At one point you have the practicality of there being a plug or a positive part which has to go into a negative part. Typically imagine if this were to be a pen, you have a cap, and going in further, imagine if this is going to be a ballpoint pen, and in case of a ballpoint pen, the refill has to go inside. So specifically every type of refill, every type of pen, the allowable variations in production are mentioned here. Now what do we talk about these things? Once in a while I gather these things. While it does not look very attractive, the reality is this whole thing has been mounted with 4 holes on one side, and again coming back to the features, on one side at one corner here we have a heat sink, and there are mounting holes on the heat sink. There are 2 mounting holes, and the heat sink goes, and then all these power devices are supposed to get assembled on the heat sink, and they share a common a base which has to be fixed here. Now this is where the process planning also comes in picture, saying do we first mount all these things and then try to push them inside? Alternately, do you push all of these things inside and do everything, and then how do you assemble the screws and all that? So for this, standard practices are there, and standard jigs and fixtures are there. So typically, most likely that all these participating components are probably mounted on the heat sink up front, and they are all aligned with respect to something which simulates the pitch of the screws here. You have seen here, if you see the pitch of these lead-in hole components, and imagine you take a another metal plate or anything, drill all the holes, you can push all these power devices into that and then align all of them, then mount these. I do not know whether there are transistors or thyristors, you have to mount them inside. Once they are aligned perfectly, then naturally they go off into this, which is part of the design process. While the first 10 lectures spoke a little about how they try to just conceive a product and push it down, from the second side talks a lot about how to make them manufacturable. So specifically I have given this example of saying we have 5 different loose components which are to be mounted on a separate mechanical assembly, and all of them have to go inside. Fortunately for us, we need not worry too much about it, because there are process planning people who know how to handle these things. Most likely they have already fixtures or jigs to hold these things. Single component, there is no issue about it. There is a single component which is mounted directly onto a small heat sink, and at the back the same mounting hole which is used for mounting the power device onto the heat sink is also used for mounting this inside. Now comes to why I continue to show these things are, we have several other things. There is a small header here which is part of a connector, there is one more here, and there is one which is very close to here, and there are some little larger power connections here. All of them are once again mechanical items, and this is where the criticality comes. How do you mount all these things? How do you position these things on the PCB? This is where I feel our course and let us say registrants to this course will benefit a lot if upfront you sit with the designer of this or fabricator of this PCB and find out typically how well it is convenient for us to use it. In this case, fortunately, there are no trimmers and such things that need to be adjusted, but however, all this stuff now has to now align itself to an enclosure outside where you probably need access inside. Look at it here. One more time, I have ended up with why I have found this out, two peculiar some device here which I do not know if it is a fuse or it is a some gas discharge device or something like this, which probably you need an access to it from outside such that when you want it you can isolate it, or when you do not want it you can remove it. Oh, right now it is frozen, I will leave it like this. Later on I will tell you. Most likely it is a some sort of a device for which need access, and by definition this is not a user serviceable thing. In case something goes, the whole module will be taken inside, somebody has opened it, probably they have a screw here or some device to clamp it and remove it outside. This is where extreme thought and interest is required for us to make these things. And then I will again draw your attention to for small diodes which are mounted here, power diodes. Generally in the case of these devices, the heat conduction is probably through the leads. However, due to some I do not know peculiarity of this, they have provided a small slot here. A small slot probably helps in a little bit of air circulation, or it prevents charring of these diodes, charring of the PCB and diodes in case of some failure. Similarly, you have seen this, there are very large tracks, pads and all that here. All these large tracks and pads need to be reflected in your model. So, it helps if you try to start your solid model including these things like power components, while in the case of a routine small device they may not make too much sense. In the case of our little larger things, wherever a current of more than 1 amp is involved and you have large electromechanical device, this is a bank of relays, and these bank of relays, it says, of course it says 7 amps. 7 amps is not DC breaking, neither it is service rating, it is just some nominal rating, and the person uses it, he knows what to do with it, but it can safely carry 7 amps. Once the circuit is switched, and it can continue to carry 7 amps without any problem, provided it is within the voltage setting and within that what do you call other specifications which are mentored here. But most important is what is the spacing you require to be kept, and secondly, do you need some a little bit of circulation, and does this become hot? In case this becomes hot, any other component here by radiation will probably pick up the heat from there. These come over the years by practice, and each industry and each field have standardized on these practices. You have seen why I am repeating it is, this, in spite of his being a simple electronic circuit and based on a simple circuit diagram, you will notice that eventually when it takes a physical shape, all these have to be considered, and very peculiarly, I do not know, meant for various other reasons, probably involving soldering, probably involving shrinkage, involving wicking and wetting of the various solders, various types of thermal bridges as well as dams have been built inside. If you give a gap, heat will not be shared. If you just leave a solid copper area, in this case the current will be shared. So, these things are all to be considered when you are making anything which is bigger than a normal simple 1 amp circuit. Now, I will go on to, kindly if you see my monitor again here, you will notice this is a very simple, probably the simplest, which I have already shown you earlier. You may be wondering, can we randomly give those dimensions? No. Depending on the type of application, we have things like loose running, free running, close running, sliding, locational, clearance shaft of things, and depending on the basic size, what are the variations that are allowed have been given here. You have seen this, no? These tables have been standardized. Generally, J and JS, especially JS, is what is most commonly used and preferred, because these are transitional, saying when you have a nominal dimension, most of our things can fall on both sides of it. In contrast, when you are having hole based one sided simple tolerances, H and this H are used. In the case of small h, you have seen this, always the shaft is smaller than the nominal dimension, and in the case the hole will be always bigger than the nominal dimension. So, and then the earlier slide showed you about what is the range of fits and so on. So, these things somebody has worked closely and found out how to specify a particular type of fits. So, I have come back to you all this, let me go back again. Yeah. Now, we come to, if you remember the earlier thing, much earlier I have mentioned you saying there is a limit in this, no? The shaft happens to be 0.005 nominal units. Beyond this, the lower this shows the limits with which the shaft can be accepted. A lot of it depends on the method of manufacture, and even if you start with a machining device which has the correct settings, with the wear and tear of the tools or wear and tear of or the temperature variations and all that, small variations will occur. Usually this sort of designations are used equal deviation on both sides, 1.5 plus or minus, it is actually, because it was 0.5, no, must be 0.025. This will follow within that. There is a bilateral measured equally on both sides. This one is about unequal variation. You have seen that, no? They have put 0.03 on one side, 0.05 on one side, saying it can be a little more on the positive side, little less on the negative side. And these are typically, whenever we talk about interferences and all that, one side, if you remember in that case H, small h and big H, and things fall within this. These are all standard way of designing things. Now, if you take a very complex assembly, in this case this is probably speed reducer or a gearbox, you will notice that there are so many elements here which rotate, and this 1, 2, one assembly here, one assembly here are the bearings that need to be assembled here. So, the next mention is all about, let me go back here and start with, at this point I have looked around, and then I will start with probably FAG, both the SKF and FAG are the leaders. Now, these people give, one is the application. When you go down with the application, one of the first thing you can talk about is specification, and at one point they give things about where we use this for the applications. So, various things about what is the basic dimensions and the load rating, dynamic and static loaded, and then maximum axial load, and all these things, attainable speed, the type of lubrication you use and so on. All of these the manufacturers give, usually the manufacturers mention all these things. If you go down further, the application manuals fully give details of what is the type of the tolerances which they give, the application of heat, and for high precision bearings what is the tolerance within the form, what is the how you specify various things here are all mentioned here. You have seen here saying with respect to speed, where exactly this application can be used and which is the type of bearing we try to use, and the service factor, saying bearings with steel balls, what is the service factor, and all that they have worked a lot and decided on how to maintain these various factors. This is one of the random catalogs I have picked up. Installation and maintenance guide, saying how does one actually, you have seen this, here he has talked about shaft and housing fits, saying it is very important for us to determine selection tables, how to housing fit, shaft fit, fits for hollow shafts, ISO tolerance, grade limits and so on. So, every bearing engineering manual gives all these things here. Why I am mentioning it is, you can just look around and how close and how the manufacturing follows certain standards. And if you leave, let us say you do not get any one of the original bearings, or you have opened a old housing, or you want to make alternate sources, each of these manufacturers also give you have seen this, the best 4 of them which I have managed to get. There are standards meant for even roller bearings. Now, understanding and going through these engineering manuals, it is easy for you to carry out your design. Just for just to tell you, and then that I could actually locate it. If you go through any of these catalogs, you get full details of how best you can select a particular type of a bearing and you can interchange it. While this looks very obvious and unnecessarily repetitive, unfortunately for sheet metal it looks like they are not that commonly available. However, regular professional manufacturers have standardized on these things also. So, one should be careful, especially after making your simple design, whether things which are part of these various standards are followed and you are able to utilize existing knowledge and try to make that things fit each other. So, if you look back to this big table, default tolerances in millimeters, see what all has been specified here across two bends, across formed part, across holes across two bends, hole across four bends, formed edge to hole, all these have been somewhat regulated, and this is and whenever a tolerance like this is mentioned, it is almost like a legal or binding document on the supplier. So, you need to consider all this, look it up, look up against the available what you call open documentation and try to adopt one of these things. When you adopt it, chances of your failure or surprise in what you call fabrication will full be, you can huge amount of this I had shown you earlier. So, here things like general tolerances for sheet metal formed parts, these are all mentioned. So, it is convenient and almost mandatory for you to follow one of these which other industry people follow it, and then if you follow it, chances of your going wrong will be negligible and you will not end up with this funny design which I have made. While at one level this design looks nice, another level the fabrication issues have not been taken care of. So, the whole I will take a break of this whole session here at this point, so that you will try to see how well variations and production also have to be incorporated into your designs. While solid modeling is convenient, I can make a very impressive looking thing. One way of dealing with it is probably make two of these parts, one within outside of the tolerance or just out the extreme end to one tolerance, another is the lower end to the tolerance, and see whether they will fit each other by manually trying to show them on your screen. That will only clarify your concepts in for you. And the new software, as I have told you, there are so many of these solid modeling software have this incorporated already. So, you can check between part A and part B under what conditions, what type of a fit results in this. So, if I get a chance and if I get an access to one of those things, I will try to show it to you in maybe the next lecture, saying in case you have a regular full fledged solid modeling software, how these tolerances and how these fits are taken care of. So, thank you. I will continue in the next this thing. So, thank you.